All right, so armed with this knowledge, and we're particularly interested in this bit up here, right? These were just examples. All right, so armed with this knowledge, let's start looking at this sum that we were interested in, that we're so interested in, sum n equals 1 to infinity of 1 over n to the p. So we're going to observe it as a function, a continuous function, f of x, defined in the real numbers, as 1 over x to the p. This is positive, continuous, and decreasing on 1 to infinity as long as the p is greater than 0, right? So it's a little weird. We put the p in the denominator. So like if the x was in the numerator, we would be talking about negative p's, but we're talking about like 1 over x squared, 1 over x to the fourth. That's what p greater than 0 is. So all those functions, if you graph them, look like this. That's what they all look like on the positive side. And of course, we're only interested in from 1 to infinity. So, even powers go up over here and odd powers go down over here, but that doesn't matter to us because we're only interested in 1 to infinity. And we're also not interested in the vertical asymptote because we're only interested in 1 to infinity. Our f of x is positive, continuous, and decreasing on 1 to infinity. Why? Because natural numbers, sequences have the natural numbers as their domain, and the natural numbers start at 1. So anything that happens for x less than 1, we don't care about. All right. So, so since we can come up with this function, we can use integral test. The integral test applies because we've met the criteria for the integral test, the fairly rigorous criteria for the integral test, that we're looking at functions no matter what the p is, as long as p is greater than 0, the function we get is positive, continuous, and decreasing on 1 to infinity. Therefore, we can use the integral test. All right, so what would that look like? I would have to do the integral from 1 to infinity of 1 over x to the p dx and see what that is. Well, so that's going to be the limit as b approaches infinity of the integral from 1 to b of, let's right away write it as x to the negative p dx. All right, and then I can anti-differentiate that even not knowing what the p is. Limit as b approaches infinity. Think about it. What's the antiderivative of x to the negative p for any value, any real value of p? It's x to the negative p plus 1 over negative p plus 1. That's the antiderivative. So just raise the exponent 1, divide by the new exponent. All right, but I didn't know what the exponent was. I used a variable for it. All right, but here's an important thing to observe, though, right at this point. P cannot be equal to 1. B can be equal to 1, or the lower limit can be equal to 1, but P cannot be equal to 1 because then the denominator would be undefined. So this is only for P not equal to 1, and so if P equals 1, we're going to have to do something different. So we're going to find out about all positive values of P except for P equals 1. All right. Also, by the way, if P was equal to 1, then the antiderivative wouldn't be this. If P was equal to 1, what would the antiderivative be? It would be ln of x. So, and that's how we're going to handle that case separately. We're going to handle all these cases. We're going to handle every real number except 1 right now. All right. So one thing I did was factor out the negative p plus 1, and I also wrote it as 1 minus p because it's just easier to write 1 minus p than negative p plus 1. I factored that out because it does not depend on b. And then I have limit as b approaches infinity, and b is the limit variable. So the fact that the 1 over negative p plus 1 does not depend on b means I can factor it out of the limit. If that expression is factoring out had a b in it, I could not factor it out of the limit. So you can only factor things out of the limit that do not contain the limit variable. So this p is, in a sense, fixed with respect to b. All right, and then I have b to the negative p plus 1 minus 1 over 1 minus p from 1 to b. All right, and then so that's going to equal. So we'll just do the limit of this part, and this part we'll just evaluate. So I'm going to have 1 over 1 minus p times the limit as b approaches infinity of b to the negative p plus 1. And then that's plugging in the b. Does that make sense? Oh, I see. I already plugged in the b and the 1. All right. Did I? What did I do there? Oh, I see. So because I already plugged in the b here and the 1 here, That's why we actually don't have the 1 to b there, because I already plugged in the b and I already plugged in the 1. Yeah. Confused myself with that one. Now, for the second term here, I'm distributing this 1 minus p that I factored out. This is 1 over 1 minus p. So I'm going to have 1 over 1 minus p squared. All right. Now, whether this converges or not depends on this limit and nothing else. All right. But this limit is one of these, right? Because the limit as x approaches infinity of x to the n. The limit as b approaches infinity of b to the negative p plus 1. All right, so this limit is going to be 0 if the exponent is less than 0. The exponent is negative p plus 1. So this equals 0 for negative p plus 1 less than 0. All right, so if the negative p plus 1, which is our exponent is less than 0, then the limit is 0. So this limit is 0 if negative p plus 1 is less than 0, which is the same as saying p is greater than 1. Right? And also, by the way, this limit is equal to infinity for negative p plus 1 greater than 0, right? Because then I would be looking at a limit as x approaches infinity of x to the n, where the n is greater than 0. So the negative p plus 1 is playing the role of the n. Greater than 0, we're going to have a limit of infinity. All right, and that, by the way, is, we could put the p to the other side. That's, whoops. What did I do here? Oh, greater than, right? Because this says greater than here, I just copied it down. Funny. That's a greater than. So if p is less than 1, the limit is infinity. If p is greater than 1, the limit is 0 of this term. All right? Now, this negative 1 over p, 1 minus p squared, it doesn't matter what it is, because either this limit is going to be 0, and therefore this integral is going to be a finite number and converge, or this limit is going to be infinity, and therefore this value is going to be infinity, and the integral is going to diverge. So another way to say that is that the integral from 1 to infinity of 1 over x to the p dx converges for p greater than 1 and diverges for p less than 1. All right, this integral, if the p is greater than 1, we're going to have a 0 limit here, and this integral is going to converge. We don't know what to. We don't care what to. As long as the p is greater than 1, the integral converges. The integral is going to diverge if p is less than 1. So the result of that is, from the integral test, we now know that the sum from n equals 1 to infinity of 1 over p squared diverges for p greater than 1, p less than 1, sorry, diverges for p less than 1. Sorry. The sum, it's not late. I can't blame myself for that. From n equals 1 to infinity of 1 over n to the p, that's a p series, okay? Diverges for p less than 1 and converges for p greater than 1. All right, so these are two of the primary criteria for the convergence of a p series. P series, if I want the p series to converge, p has to be greater than 1. All right, but we still have to contend with what happens when p equals 1. That's the last value that we haven't considered. That is what we'll consider next.